when we talk about taking measurements in the lab, we can talk about our data, and we can talk about our data being accurate, and we can talk about our data being precise. So, and we have to consider those two separately because they mean two different things. Does anybody know what accuracy means? If you say your data is accurate, what does that mean? And that's not on here. I'm just asking if any of you know from previous classes.
So how close you are to the right answer?
Exactly. So accuracy is how close you are to the right answer. So it's a accuracy, and we're going to do a whole separate section on that, so don't panic that it's not up here. Accuracy is your correctness, right? How right you are in the measurements that you've taken. So then what is precision? Good. So precision, you have to do the same measurement multiple times, and it's how close those measured values are to each other. So if you are doing a lab activity and you repeat it multiple times, the same experiment, do you think you want to get close to the same answer each time? Yes. If you're not getting close to the same answer, then there's something wrong with either how you're doing your experiment, how you're taking your measurements, or how it's set up. So precision is how close your measured values are to each other. So doing the same experiment multiple times, how close your data is. And so a one-word descriptor for that, for precision, is reproducibility. Okay? Can you reproduce the same results doing the same experiment the same way? So when we talk about data and whether it's precise, so if the data is close together, it's precise. If it's not close together, it's not precise. And the problem associated with data that's not close together is called random uncertainty. So what does random mean? All over the place? So random uncertainty means you will end up with values that are too high and too low. And so if you end up with a range of values, what is that going to do to your precision? If you've got too high and too low, is it going to increase or decrease your precision? Decrease, right? And so random uncertainty is a lot of times also just called uncertainty, and it's also called random error. So random error, random uncertainty, uncertainty all mean the same thing. It means your data is both too high and too low. I'm going to scroll. So let's talk some examples of common things that you may have used before where you would experience this random uncertainty. So if you're using a ruler to measure the length of something, and you're going to measure that length 5 different times, you want to make sure you're using the same ruler, but each time you measure it, are you going to line up the end of what you're measuring exactly in the same spot? No. Even if you try, sometimes you're going to be a little bit before that, and sometimes you're going to be a little bit after that mark, right? And so those small changes are going to lead to random uncertainty. It is inherent in taking measured values that you're going to have random uncertainty. And so we want to talk about ways that we can decrease it or correct for it. A digital balance. You might think, oh, a digital balance, I'm not going to have random uncertainty because the tool's doing it all for me. But that's not true. So within a digital balance, you've got electronic components that if they're heating and cooling and not staying at a constant temperature, how they function will change, which will lead to random uncertainty. Friction between the parts moving past each other. Air moving in the room, and when we get into using the balances that measure to the milligram, so 3 decimal places, you will be able to see that. you'll be able to see the fluctuation in that milligram measurement just due to the air conditioner turning on and off, or people around you talking, or touching the lab table. So all of those things, the having them or the lack of them, and the degree to which you have them, affect how the balance functions. That is the reality of how it works, and so that leads to uncertainty. So we want to come up with ways to report the uncertainty that we expect with different measuring tools. So I would write this really nice and big, and I promise it will make sense once we talk about it in more detail. But when we're reporting a measured value with uncertainty, we report our measurement. So if we're using a balance, 23 grams, then we use the sign plus or minus, and this uncertainty, which we're going to talk about in detail, and then the unit. So if that mass of 23 grams that I was talking about, you might say that that measurement is 23, then plus or minus, let's say the uncertainty is 1, and then the unit is grams. So the measurement plus or minus the uncertainty followed by the unit. So right now, I'm just showing you the form it's writing. We still have to talk about how in the heck do we get uncertainty for different tools. And I promise we're going to go over that. Another note to make about uncertainty. So when you're reporting uncertainty, you only want to report it with one non-zero digit. Okay? And I promise that'll be clear, but get that stuck in your head. Uncertainty has one non-zero digit. So if it has one non-zero digit, how many sig figs does it have? 1. So uncertainty should have one significant figure, and whatever digit that uncertainty's in should be the same place as the last sig fig of the measured value. So we have how we're going to write it and what it should look like. We still have to talk about in detail how we get it. How do we come up with uncertainty? So the first kind of tool we're going to talk about is an analog tool. So we talked about analog tools last class. We said analog means we have to figure out ourselves what the increments mean. And so when we are reporting the uncertainty for an analog tool, the uncertainty for that tool is going to be plus or minus half of the smallest increment on the tool. So when we were reading the rulers and graduated cylinders, did we have to figure out the smallest increment to be able to read it? Yes, you already have done that part. Now all you're doing is saying, well, the uncertainty is half of that. So if on a graduated cylinder, each increment is 1 milliliter, what is the uncertainty? What's half of 1? 0.5. So the uncertainty would be plus or minus 0.5. So let's look at this ruler. What is the smallest increment? So increment means the smallest division. So the smallest division on the tool that we can read, what is it? Good. Each of the lines represents 0.1 centimeter, right? Do we agree? Okay, so now let's read what this measured value would be based on what we discussed last class. So we said we include all known digits, right? And one last estimated digit. So what can we read? 3 point I'm going to say 3.1, and then my estimated digit's going to be 9. Did everyone have to say that? No. And now, once we report the uncertainty, you'll see what a more clear reason of why I say your estimated digit is up to you. So, here's our measurement, and then we say plus or minus half of the smallest increment. So what is half of 0.1? 0.05 centimeters. So what this says is that any value that is 3.12 plus 0.05, between 3.19 plus 0.05, which is what? What's 3.19 plus? 3.24. And then what is 3.19 minus 0.05? 3.14. So what we're saying with the uncertainty is that any value between 3.14 and 3.24 are acceptable. So anything in that range would be acceptable for this reading, because our uncertainty is plus 0.5 centimeters minus 0.5 centimeters, or 0.1 centimeters overall. Does that make sense? So, all we're doing today is adding this uncertainty to the end of our measure to communicate clearly what we measured and with what certainty we know this last digit. So, measurement, right? Plus or minus uncertainty, unit goes at the end. Okay, let's look at another analog example. So if we look at this this graduated cylinder, what is the smallest increment? .2 milliliters? Okay, so let's figure out what we would say the measurement is.
Should just be 2.
Oh yeah, 2, sorry. Thank you. So when we read this, we would say what? We can read the 3, right? Then what do you say? 8? And is that 8 estimated? Yes. I can't really read because what is my uncertainty? If my smallest increment's 2, what's my uncertainty? 1 milliliter. So, we already know how to read the tool. Do we see how to figure out uncertainty? Half of the smallest increment. Yes? So now let's go back to that part where I said your uncertainty should only have one non-zero digit. So on these examples, it's not going to be that hard, but you'll see some below. This one has one significant digit. Do we agree? And do you see how that one digit is in the same place as the last significant digit of your measured value? Yes. So what we are saying is our uncertainty is in the ones place, right? So when we're reporting the measured value, our estimated digit should be in the ones place, right? If we include all known digits and one last estimated digit, our estimated digit should be in the same digit or place as our uncertainty. Okay? Okay. You guys try this one. What's the smallest increment? 1 milliliter. And so when we read our measurements, our measuring tool, what are my known digits? What can I see? 4 and 4, right? And then what did you guys say is the estimated digit? 0.9. Then plus or minus, what's half of 1 milliliter? 0.5, and then the unit goes at the end. So do I have one digit for uncertainty, one significant digit? And is that digit in the same place as my last significant digit of my measured value? Good. Now, did everyone write 44.9? No. Huh? Okay. Did you have 45.0? Okay. So anything, when I'm grading, anything between 44.4 to 45 point, wait, did I do that right? Why can't, yeah. Anything in this range would be acceptable because our uncertainty is 0.5 milliliters, okay? So now let's look at digital tools. Digital tools are easier, right? Because you don't have to look at the increments. You do still have to communicate uncertainty though. So when we're using a digital tool, we're still going to write measurement plus uncertainty, plus or minus uncertainty, and the unit at the end. But for a digital tool, our uncertainty is just going to be plus or minus the smallest division or the smallest reported value. And we'll look at that. So I'll give you a few minutes to write this, and then we'll go over a few examples. Okay, so let's look at this balance. So we've put a quarter, someone has put a quarter on the balance, and we see that the value that the balance is reading is 5.67 grams, right? So when the balance reports this value, it's reporting the estimated digit. So what do you think the estimated digit is? You think it's the first one or the last one? Last one. So the 7 and 5, oh no, and 5.67 is the estimated digit. So this is our measurement, then plus or minus, what's our uncertainty going to be, do you think? We said plus or minus the smallest division. So that is going to be 0.01, because that last, the hundredths place can go up by 1. And then what do we put at the end? The unit. We got a temperature probe here. So it's reading 32.1 degrees Celsius. So what is the estimated digit here? The 1. So our uncertainty is going to be plus or minus 0.1 degrees Celsius. So in all ways, with what we've seen so far, the uncertainty that we're reporting just reinforces that we're reporting our measured values the correct way. And so in a lot of ways, it's redundant, but we're going to practice it because it's required in the IB Sciences, and it's a good habit to get into. Because you could get into tools, like a digital tool where the uncertainty isn't just one increment of the smallest division. So there will be exceptions. We'll have analog tools that only have one increment on it. So we have to find out from either the actual measuring tool or from the manufacturer what the uncertainty is. Okay. And then also along these lines, oh, I don't want the keyboard. There are human limitations. There are things that you're going to do where you use a stopwatch, where you're using your judgment, and there's a limitation to that, right? If you're using a stopwatch, are you always going to press stop right when you need to or start right when you need to? No. Sometimes you'll start a little before, sometimes you'll start a little after, and that's going to lead to uncertainty. And so anytime you are making a judgment, there's a uncertainty associated with it. So reaction time with a stopwatch is one of the main ones we see. And you can generally say it's 0.5 seconds or 1 second.